Okay, hello, it's me again. I'm continuing on, and remember the other day, or in the other note, I guess, I said that, that whole rule of electrons in the outer shell was okay for now. Well, now we're moving into quantum theory, and this is where we realize that there's something different about electrons. Electrons aren't necessarily particles or waves, kind of like light. They have particle-like properties, and they are made up of lots of energy. So anyways, there's this whole weird stuff. I'm not going to go into it, but we have the Heisenberg uncertainty principle, and I'm going to attach a few videos about this and a few other parts of the new quantum number theory of the atom. So we move on, and instead of having orbits, specific areas in which the electrons travel in, now we have what are called orbitals, and it's a specific three-dimensional area where an electron is likely to be found around the nucleus of an atom. And so these areas are basically electron clouds now, and the electron is moving all over the place, and we can't say exactly where it is, but we can say with probability that it's in this area. So within an atom, every electron is going to be described by 4 specific quantum numbers, and no 2 electrons within the same atom can have the same 4 exact numbers. And so here's, the new model. There's your nucleus, the red dot there, and then the electrons are zipping around in this cloud, taking up all this space. So again, we're going to talk about this one. This one is another video I'm going to show you. So it'll be attached in the links when I send out the video and my email to you. So the 4 quantum numbers, the first one is the principal number, and that's the one you are actually familiar with. And that is when you look along the side of the periodic table, you can see the periods 1 to 7. And so the principal number is referring to kind of which period it is in, but now it's in energy level. So your energy level 1 all the way to energy level 7. Next, we have the secondary number. This has to do with the shape of the orbital. And so we actually have 4 different shapes. We have sharp, principal, diffuse, and fundamental. And so instead of actually using the numbers, most people in chemistry use the first letter of each of the names of these shapes. So you have S, P, D, and F orbitals. And again, remember these electrons are moving around, taking up space, and it basically looks like a cloud. The S orbital is going to hold 2 electrons, so they're going to pair up in the S orbital. The P orbital can have 6, so you're going to have 3 different regions, each which can have a pair of electrons, so a total of 6. The D holds a total of 10, which means there are 5 different regions. And then the F orbital has 14 electrons, so there will be 7 different regions. And on the next page, I've kind of drawn all the way up to what D would look like. I didn't do F because it'll be too much. So there you go. There's the S, the P, and the D. And the way it works is you can see in this P orbital, there's actually 3 different subregions in that one orbital. That's why I put them in different colors. And so holds 2 electrons, 1 pair for the S. It has 2 electrons per subshell, total of 3 pairs. And then we have 2 electrons per subshell and 5 pairs. So that's the SP and D orbitals. Again, I didn't show you the F one because it's a little crazy. So the next one in the numbers, the third number is the magnetic number. And it's basically telling you which subshell the electron is hanging out in. And then finally we have the spin number is telling you which part of that subshell the electron is hanging out in. So I'm using the p orbitals right now as the example. So if you have the magnetic number tells you it's in this specific orbital, and then the spin number is telling you, well, which lobe is it hanging out in. All right. Again, another video I'm going to attach for you guys. And one more about the Pauli exclusion principle, and that's the idea that every electron within one specific atom has no 4 numbers the same. So we have some rules here for filling orbitals because we're actually going to draw these orbital diagrams. So we have the Pauli exclusion, the Aufbau, and Hund's rule. And to copy them, all you got to do is pause and see it. I have another video here which is attached to this, but it kind of shows you the order in which you fill the electron shells. So there you go. And here's the periodic table laid out in terms of if you find an atom here, it means that it's filled its 1s and its 2s orbital, and it's finishing off right there. If you find one way down here, these guys fit into the periodic table starting after the 6s, and then it goes to the 4f, the 5d, 6p, 7s, 5f, 6d. So that's the order it goes in. And so if I look at something like xenon, okay, so there's xenon. So if I look on the periodic table, there it is. So if I go back to the other diagram that I have, okay, we said it was right up here. And so you can see where it ends in the 5p orbital. Or sorry, it actually is in the 6p orbital. Sorry, we're looking at lead. My bad. Sorry. And anyways, it's just like xenon, but then it also fills all the way up to where lead is. So lead actually hangs out right there. And I'll show you that on the next one. There's the lead right there in the 6th level. And so it ends in the 6p, and it's 2 spaces over, so that's why we see 6p2, and then go back 5d10, and then the 4f, as I said, fits in right here. So 4f holding all 14, the 6s2 having 2 electrons there, and then everything else is the same as xenon because it starts right there and has all of the same. And I think you could possibly try doing the silver if you want. Now I'm going to stop there, and I'll do another video because these things will end up too long if I don't stop it here.